Good afternoon and welcome. I'm Rick Carney, coordinator for the Great Basin Landscape Conservation Cooperative. For those of you who might be new to the Landscape Conservation Cooperatives, or LCCs, we are a partnership among public and private groups that are working together to meet large-scale conservation challenges across the 5-state Great Basin region. We have supported a variety of science and conservation projects on high-priority topics. This webinar series highlights a few of those projects, plus some more. We hope that these webinars can provide a platform for discussion about research and its application to the issues in the Great Basin. We will keep today's presentations relatively short, about 30 minutes or so, and reserve the second half of our hour together for questions and discussion with the presenters. Since there are quite a few people who are on the webinar today, we won't have an opportunity to ask questions directly, but we do ask that you, as you have questions, that you type them in, and we will read those to the speaker at the end of the presentation today. Today's webinar will be recorded and available on our website. Please, if you're not speaking, put your phone on mute. On your screen, you'll notice a small collapsed control panel in the upper right corner. By clicking on the small arrow, you can expand the control panel. In this expanded control panel, you can send in your question. Simply type your question into the chat area near the bottom and press send. This question will be sent to us to respond at the end of the webinar, as I mentioned. I would now like to introduce today's speaker, Dr. Lorraine Flint. Lori Flint has a PhD in soil physics from Oregon State University and has been with the USGS since 1986. Recently, she has been involved in investigating the influence of climate change on snow processes and water availability in the Western US. Her current research involves downscaling future climate projections to ecologically relevant scales, that is, to the 1 kilometer or 30 meter scale in some cases, and using that as an input to derive hydrologic response for projects throughout the Western US. And these are used in analyses of water availability, flow and transport, snowmelt processes, and ecosystem change, for example. With that, I'd like to turn the microphone over to Dr. Flint and ask her to share her results of her work with us. Lori?
Thank you very much. I'm going to talk today about some work that we've been developing for about a decade now to be able to turn climate change into hydrologic response. And we've applied this to the southwestern US and a number of other places as well. So we're trying to, in recent years, we've had many opportunities because of the ongoing changes in climate that it offered us abilities to test these models. Click, go, okay. And there's nothing like extremes to create opportunities for model development and testing. So I know that the Great Basin also had a drought that was pretty extensive. We know that the eastern part of the country has had a horrific hurricane season, and these kinds of events are what have allowed meteorologists to really refine their tools and do a better job of forecasting. This was the worst fire in California's history, but it's been occurring across the whole western US in unprecedented numbers and levels of intensity. And there have been, our tools have been used in a lot of cases to correlate to wildfire risk across the western US. So changes in climate and increasing air temperature and extremes in precipitation, both wet and dry, are creating novel hydrologic conditions across the Southwest. The Southwest is unique in its climatic complexity, ranging from hyper-arid deserts to coastal fog zones and increasing numbers of atmospheric river events. The climate is creating challenges to maintaining adequate water supply and sustaining our forests, our landscapes, and biodiversity. We need to have tools to help inform natural resource management at multiple scales, from regions to watersheds to hill slopes, And these tools need to address both watershed hydrology and regional landscape ecology. They need to provide historical analogs so that people can compare them to things that they know in the past and look into the future for projections. And they need to rely on deterministic processes to help to reduce some of the uncertainty. Water balance modeling can be used to translate climate change into impacts on water supply, landscapes, irrigation demand, and ecosystem stresses. It can be done at a regional scale, but maintain fine spatial resolution. And these can be used to do scenario testing that can evaluate impacts from things like land management, urbanization, wildfire, or vegetation changes. I'll touch on a broad range of examples and hopefully span the range of people's interests in the talk today. We'll start with conceptualizing a simple water balance model that describes hydrologic processes across large regions, and then describe the model itself, how we calculate the water balance. We've been doing some model refinements in the last few years and calibration. I'll show some examples from California and the Great Basin. And then a couple of applications in the Southwest, as well as future directions. So these are the components of the water balance. You basically have inputs with precipitation, snowmelt, evapotranspiration, and sublimation are outputs. And then what can get into the soil profile can become recharge. And if the soil is full, then the runoff will occur. So it all adds up into a water balance, and you have changes in soil water content. So it's really dominated by what's going on in the soil profile. This is our model schematic that shows the different modules in the model. We have our inputs in the top, which is the snow processes and climate, and a detailed energy balance model. Once you get through that part of it, the water then goes into the soil profile. So the soil profile is central to calculating the water balance, and getting that data accurate is really important. So each of these then components can then be calibrated, so we can reduce some of the uncertainty in how the whole thing operates. Once the water gets through the soil profile, then recharge and runoff can be combined to calibrate into basin discharge or stream flow, and then groundwater recharge. One component of the outputs of the basin characterization model is the climatic water deficit. This is the annual evaporative demand that exceeds available water. It's potential minus actual ET, so it's really controlled by air temperature and PET and the soil storage. It integrates climate and energy loading and drainage and available soil moisture, addresses irrigation demand, and defines the level of stress on the landscape. This variable has been used extensively throughout the Western U.S. to correlate to species distributions, to wildfire risk, to forest die-off, and other things like that. You can see in the graphic, the supply is our rainfall or snowmelt, and as it diminishes in the summer, you get increases in actual evapotranspiration that then use the water out of the soil. As the soil moisture declines, you can start developing a deficit. It's calculated as a deficit of what the environment could use if it were available. That's correlated to irrigation demand directly, because that's the deficit is what crops are intending to use to keep them going at potential evapotranspiration. If you have earlier snowmelt in the season, you're going to get a bigger deficit. If you have a hotter year, your PET is going to go up, you're going to have a bigger deficit. It looks like this on the landscape. This is the San Francisco Bay Area basins, and you can see the Central Valley has a high deficit and the coastal basins have a low deficit. So I'm going to use that example later on, so I needed to introduce it now. But one of the results of the BCM is runoff. This is done we've done this historically for all 4 of these regions. And California and the Great Basin, we've also done it for a series of future climate scenarios. We've just finished Lower Colorado with 2 scenarios. So we've got them all in different levels of process. This output is at 270 meter spatial resolution. That's about 18 acres, so that you can zoom into a hill slope or a small watershed, as well as looking at it on a regional basis. Each of these locations across this big landscape has their own unique hydrologic issues. So this is runoff. Now these scales were the same, and you saw a lot of those colors go to orange. So there's more runoff than recharge across the Southwest, but in many of these regions, recharge becomes a really precious commodity, and I'll discuss that in quite a bit of detail in the future, especially in a changing climate. So I'm going to show you some examples of model calibration. Some components are more easily calibrated with measured data, others not so much. Since we rely on monthly gridded climate, calibration of all the various components sort of starts with the energy balance. These are comparisons of modeled potential ET, daily potential ET, to station data. And you can see variations due to cloudiness, which we've captured quite well. Now we've compared these kinds of things across the entire Southwest at all of these different data points. And I'm zooming in to a topographically complex location at Yosemite National Park to show you how potential ET varies across the landscape due to topographic shading. So we've also compared it. This is just comparing it directly to measured to modeled, and you can see it for the different months across that entire region. We're also looking at calibrating snow processes. We've done this in a little more detail in California than the rest of the areas, but the variables have been distributed across the landscape. This is calibration for snow-covered area, so we can look at how we can match in an accumulation month in February and how we can match the melt season. This is for the Sierra Nevada. Also looking to be able to represent glaciers. So these are this is a glacier database that we've been able to match quite well across the regions. And we've also used snow coarse data to be able to calibrate to snow water equivalent. So this is just a series of snow courses. There's 87 of them that we've been able to use to optimize the spatial distribution of our snow parameters that we have to calibrate to. And then the last thing we do is look at the timing of runoff to proof the snow module. So this is where we have used recharge and runoff to compute basin discharge, and then looking at it on a monthly basis to be able to see if we have the shape of the curve correct. The water balance is contingent on the soil water storage and how much water the vegetation can use. We've not developed the calibration to actual ET for the entire region yet, just for California, and I'll show you some of that later. But the development of soils across this whole region has been really critical to getting the recharge correct. Soils data is available from the NRCS, and you can either extract the maps for the calculated hydraulic properties directly, such as water content at field capacity or wilting point, or you can develop them, which is what we ended up doing. These values are often, these values of 0.03 megapascals and a wilting point of 1.5 megapascals are most often used. We discovered some issues with this when we were working with the Great Basin. So we were trying to test recharge results and hone in on recharge because that's really important in the Great Basin. And there were very few measurements of these, but we came up with some measurements across the basin to try to test the model and to see how well we could do to match recharge. These were the basins we were looking at. And the background map is the map of recharge that we originally developed. So in doing so, we noted, so the two figures here are the same, one's linear and one's log, so you can see the low values. The black dots are our modeled estimates of recharge for those basins. And all the colored dots are a series of different kinds of measurements. So we have estimates of recharge from calibrated groundwater models. We have chloride mass balance estimates. We have estimates from recharge runoff modeling and mod flow. So you can see that we're overestimating recharge throughout this entire region. Well, one of the reasons, aside from the hydraulic properties, is that the Surgo available data set limits its soil depth at 2.01 meters. So we did 3 different things to try to ameliorate the fact that we're off here. First of all, we used texture, which is also available from the Surgo data set, to estimate field capacity and wilting point. We ended up using a 0.01 megapascals for field capacity and -3 megapascals for wilting point. So we have more plant available water. If we're overestimating recharge, we need to be able to get rid of some of the water by evapotranspiration. So if you have more storage in the soil, there'll be more water available for the plants. So then additionally, we added organic matter to the calculations to further increase the water holding capacity. As you can see in this, for the series of different textural classes, if you add organic matter, your soil water holding capacity goes up for everything except very clayey soils. So that allowed us to get, if you look on the left, this is an example for the Upper Colorado. This is soil storage. And the left is the original hydraulic properties, and the right is calculating them from texture. You can see increases in storage across the whole domain. And similarly for California. So then finally, what we noted we had to do in the Great Basin, on the left-hand side, we see soil properties. On the right-hand side, we see geology. Now the yellow is in the basin and range, and those are the alluvial deposits in the valleys. So knowing something about this, we disregarded the soil depth limit of 2.1 meters depth that was available from the database, and instead said that whenever the soils were 2.1 meters and they were mapped as quaternary alluvium valley fill, we would assign a depth of 4 meters instead. This, having worked in the Great Basin for many years, this made a lot of sense to us. And then the last correction we made, and this was one of those opportunistic things from having measurements in the ground when we were having a drought, is our soil moisture sensors pointed out to us that we were actually drying the soil out in 2012 and 2013 below the soil water, before the soil wilting point. So it's drying it out below how much the plants could take out. This is typically not done in models, and this was something we had to revise in order to be able to dry the soil out below that. This only happens in very dry years, but you can see our model results are matching that decline below wilting point. So back to this graph again, where you can see that we're not doing very well, and when we change those 4 different things, all of a sudden we're splitting the difference across all of those measurement points and doing a much better job of matching it. So I'm going to go through and talk about some different applications. We can run the model for the historical climate record and for the futures. I've shown you the regional recharge and runoff averages as maps. So we can also characterize the water balance components that we've talked about. So these are basins across the Great Basin, from the north and the top graphics, to the middle of the basin, all the way down to Lake Mead at the southern end of the basin. And these are the different components. So you start at the bottom with the soil storage component, then you have snowpack in white, recharge in dark blue, runoff in blue, actual evapotranspiration in green, and then the climatic water deficit is in red. And so you can see as you decline in the amount of snow that a valley has, you see that the water deficit gets bigger and bigger. Snow is that thing that extends the water supply later into the season. And so if you have less of it, you get more of a deficit. This is what's going to happen when we actually start losing snow in future climates. You can see the difference in soil storage is related to the amount of evapotranspiration. And you can see that there's some places are very little recharge in comparison to runoff. So we ran these models for future climates. We went through a very long process to decide which future climate scenarios from the 112 that were originally available best represented the range of projected conditions. And we were trying to do this for all 4 of those big regions, so the Colorado, the Great Basin, and California, so that we could have coincident models run across each region. So this was done by Stu Weiss. He used a cluster analysis approach that allowed him to get the seasonality of the precipitation and the different air temperatures. So this graph is showing on the y-axis projected change in precipitation. You can see above the 0 point is increase in precipitation, and then below is a decrease. And then all of the models are projecting a increase in air temperature. That's the x-axis. So you can see the range of conditions that the projections represent. And we have two scenarios. One is the business as usual scenario, that's an RCP 8.5, and the mitigated, which is the RCP 4.5. So there's 6 models and 2 scenarios for a total of 12. And we've run these for California and the Great Basin. So I'm going to give you a couple examples from this wet one in the green box and a dry one down in the red box. So here's this is a map of the Great Basin. The one on the left is the wet scenario. The one on the right is the dry scenario. They're both business as usual emissions. And the precipitation difference is calculated as 30-year means, where we're subtracting the end of century from the historical. So you can see that on the left, we're getting an increase in precipitation with the wet one, even though then there are some places that don't have an increase. And then on the right one, you can see mostly a decline in precipitation. But even though it's a dry scenario, there's areas in this that actually still have increases. And you're seeing increases of up to 100 millimeters per year. So that's a big range across there. Now we know that air temperature is going up in all cases. So water deficit, this is a water deficit for the same with the wet on the left and the dry one on the right. It's dependent on air temperature and evapotranspiration. All scenarios agree that temperatures are going to rise. It just depends on how much. So the water deficit goes up in both scenarios, indicating more environmental demand for water and irrigation, stressed landscapes leading to wildfire risk, and likely changes in vegetation types. So this is a map of the current recharge, 30-year mean for the Great Basin. You can see averages of about, from 5 to maybe 25 or 30 millimeters per year across the region, with the exception of the Snake River Plains, a little bit more. It's got much more snow up there. So if we look at that current recharge and then we say, what's the difference into the future, we can see that the wet scenario, there are still places with losses of recharge due to warming. And in the dry scenario, there's places with increases in recharge because the warming causes more ET and there's more room in the soil for the recharge. Those same locations are locations where runoff will go down, coincidentally. Also note that the basin fill areas have little change regardless of the scenario. So we can also look at time series. The center of the graph is current. So if you look at the time, it's going from 1940 through 2099. And so the left-hand side is historical, right-hand side is future. And this is the lower Humboldt, which is about midway down to the northwest a little bit. You can see the hot, dry future has declines in precipitation, and the warm, wet has increases. You also see that the warm, wet increases are a little spikier, so you have some more extremes. In all cases, temperature is rising, a little more so in the hot, dry future. Snowpack is pretty much gone by mid-century with this scenario. And with the wet scenario, it lingers on a little bit longer, but it's still almost zero. And the water deficit goes up in all cases. Now we look at recharge and runoff for the same situation. You can see that really big spikiness in the warm, wet future. You also note that you don't see a whole lot of changes in the recharge as much as you do the runoff. The recharge, and I'll show you some more graphics showing this, the recharge actually is more resilient in the with changes than the runoff is. So this one is looking at the same set of graphs, but for the very bottom of the Great Basin where it's hotter. So this is the lake mead, and you can see slight decreases in precipitation in the hot, dry future, and in the wet future, you see those spikes again, where you have a lot more variability and increasing precipitation. Temperatures all go up, and doesn't start with much snow to start with, but it pretty much is gone by early in the century. And water deficit continues to go up as well. And if we look at the recharge and runoff for this, we can see a really big impact of warm, wet future in this. I suspect that this has something to do with the representation of the summer monsoons in the southern part of the Mojave. So another application is rangelands and climate resiliency. This is being done for California's 4th climate change assessment. And this application is looking how soil management can change hydrology. So what can somebody do to manage their land to make it resilient? And the idea is to improve the soil health by increasing organic matter, however you choose to do it, whether you add compost directly or how you strategically manage your land with grazing. It reduces landscape demand for water, so it reduces that landscape stress because it keeps water in the soil. It increases the soil water holding capacity. So you're keeping water in the soil, and you keep the water in the soil, you can grow more forage. You increase recharge, and you reduce runoff. So basically, you're keeping water in the watershed. This is a study area. It's all of California's working lands. We use the BCM to simulate improved soil health due to the addition of organic matter. So we now have organic matter in our soil properties, so we can just increase that certain percentages. So in addition to hydrologic benefits, this also results in carbon sequestration. So it's a win-win kind of endeavor. We added different amounts of soil organic matter to the soils and ran a model. So these results are all in acre feet, and this is averaged over the whole state. So we have base case and the addition of increasing amounts of organic matter. So if we start over on the right, the soil moisture storage, you can see, increases. So because soil moisture increases, we get more recharge, we get less runoff. The actual ET goes up because it has more soil moisture, so you get more net primary productivity. And the water deficit goes down because soil stays water stays in the soil longer through the season. You can see some pretty big changes across the state in terms of if you were to do all of the working lands, you could get on the order of 5 million acre feet increase in soil moisture storage. So an example of what that looks like is here. This is for water year 2010, kind of an average year. This is the upper Sacramento Valley, and the little red and blue line thing there is the California Rangeland Coalition boundary. So, and the Central Valley is the gray stuff in the middle. So the one on the left is the ratio of recharge to runoff. Remember, we're trying to increase recharge and reduce runoff. So using the originally mapped organic matter, we have the blues and greens are locations in the map where recharge is higher than runoff. And the places that are oranges are where runoff is higher than recharge. When you increase the organic matter by 2 degrees, 2%, all of those values go up, except for in the middle, there's a really dark orange. That's really clay. You remember my organic matter increase doesn't work in very clayey soils. So you can see that there's increases of up to 100%, basically, increasing the ratio of recharge to runoff. So this has increased the recharge in all cases, variably across the landscape, that helps managers understand where they're going to get the most bang for their buck. So they can look at this, test the properties to make sure their properties really do match what our properties were. They can say, this is where I'm going to do the best advantage to adding organic matter to my soil. Another example, how does fire impact hydrologic resources? Well, we're going to look at the influence of fire on hydrology just with one example, and this is in the Santa Clara River watershed in Southern California. So I'm going to show a couple of examples of the ranch fire in blue and the copper fire. And where the study is looking at recharge and runoff as ecosystem services. I know there's lots of other ecosystem services, and water contributes to many of them as well, including things like recreation. But in this case, we're going to describe recharge as the water that makes it below the root zone, where it may become base flow in the summer, sustaining riparian areas and fisheries, and in locations with losing streams may become groundwater recharge. Runoff, alternatively, occurs when the soils are saturated or precipitation intensities exceed infiltration capacity. Water runs off to streams and reservoirs in the wet season, so it's a source of water supply. However, it may carry sediment and other contaminants, and it can leave the watershed, so you lose it completely. So what we did was manipulate this is just a sensitivity analysis. We manipulated the actual evapotranspiration to simulate the removal of vegetation due to fire. We used the perimeter of the ranch fire, and we used the climate for when the fire was. The fire was in 2007. So the top panel assumes that there's no fire with 100% vegetation for all of the years, the pre-fire year 2006, and then for 6 years post-fire. Here you see a big variation across the years, with the beginning of the drought shown here in 2012. In all years, runoff exceeds recharge. The bottom panel assumes a scenario with baseline conditions prior to fire. So there's 100% vegetation. And then during the fire, we take out all of the vegetation. So there's no ET. 1 year post-fire, we have no ET. And then we increase the ET by 20% each subsequent year, as if vegetation was growing back. In all years, so the fire occurred in a very dry year, and both recharge and runoff increased above baseline conditions all the way until 2012, the beginning of the drought. Recharge is higher than runoff in every case except the very high precipitation year of 2011. So our conclusions from this study, which included 7 other basins and several other analyses, was that the removal of vegetation and the associated evapotranspiration due to fire provides increases in recharge and runoff, maybe temporarily, with recharge increasing more than runoff, except for the very wettest years. Hydrologic recovery ranged from 2 to 4 years for the 7 watersheds we analyzed, and recharge and runoff were found to be easily as sensitive to large variations of climate as they are to fire after 2 to 3 years post-fire. Next example is looking at recharge. I keep talking about recharge, and we're going to look at it for the Russian River Basin with the groundwater basins outlined. Note that for some locations, however, the recharge may be enhanced by runoff in adjacent uplands that may lead to mountain front recharge. Now you can see a lot of variation in this map. There's some places where there's very little recharge. This is because the bedrock permeability is very low. And there's places where you have 3 times as much as other locations. If as a manager, you want to understand something about where those locations are and how sensitive they are to change. So if we look at the future, here we have 3 scenarios: a high rainfall, a moderate, and a low. And you can see the differences in the different maps showing which places actually respond more to changes in climate. So the valley, the central valley area right there, actually changes more than a lot of the other locations. But there's places there that stay green. And those are places you might want to consider targeting as prioritizing land management to maintain these as sustainable recharge locations. Now, I showed this a little bit before with the other graphics for the Great Basin. This is adding up annual runoff and recharge for the Russian River Valley. The runoff is blue, the recharge is orange. The left-hand side of the graph is historical, right-hand side is future, and then we have our 3 scenarios ranging from high rainfall to low rainfall. You can see that the recharge stays fairly stable across all three futures, whereas the runoff is very spiky in the top one and very low in the bottom one. And the take-home message here is that recharge changes less than runoff across all the futures. Recharge is more resilient. And another example here, we were going through the drought in California, and I'm sure that you in the Great Basin did the same things. Everybody kept saying, are we out of the drought yet? Are we out of the drought? So in 2015, we'd gone through these 4 years. 2015 had the lowest snowfall in historical record, even back to paleoclimates. And everybody's saying, well, what's going to happen in the next year? So we're running all sorts of analyses trying to figure this out for people. And then they came up and they said they were going to have an El Nino, and everybody got very excited. So it was gearing up to be a big wet year, and everybody had hopes of ending the drought. So what happens? Well, yeah, we get a lot of rainfall, and all the reservoirs start filling up, and everybody's happy, and we actually lose some of the conservation measures that people say you don't even need to conserve anymore. So were we really out of the drought by the end of 2016? Well, we did an analysis, and the graphic on the left, we are representing water supply as recharge plus runoff. The one on the left is the average annual. The one on the right is if you take the difference between average annual for every year and add them up and divide it by the number of years. And what this is the number of years of average conditions that it would take to get you back to normal. So as of the end of water year 2016, after we'd had this big wet El Nino, we have locations in the south that are still 3 to 3.5 years behind normal, and places in the north where you're still about a year behind normal. So after that big wet year, even though the reservoirs were full, there was lots of water deficits still needed to be filled. So you have shallow and saturated zones, you have headwater tributaries that aren't flowing, even though the reservoirs are full. And the next one is looking at the landscape part of this. So this is landscape drought, and we're defining this by the climatic water deficit. So on the left, we have the average annual water deficit, and the right is the years behind it would take to make it back up to normal conditions. And you can see the places in the very high Sierras that were the most impacted by lack of snowpack. These are the ones that are still up to 3 years behind. And this is after a nice big wet year with a nice big snowpack. A lot of the places are still about a year, maybe a half a year behind even after that situation. So all of these oranges and yellows that you see here, those correlated very well to fire risk locations where we had a lot of dying trees in 2015. So lastly, we have ongoing model development where we're looking at, we have recent research that provides gridded estimates of actual ET. And this has allowed us to incorporate vegetation-specific seasonal evapotranspiration. So this is helping to constrain another component of the water balance, and this reduces the uncertainty in recharge estimates. So here we're showing matches of our modeled actual ET with gridded estimates. The gridded estimates are a national product that USGS developed on the basis of remote sensing, energy balance calculations, and water balance closure for the whole US. And you can see we're matching different vegetation types that have different seasonal patterns of ET. This is allowing us to do things like have species-specific disturbance or type conversions or having wildfire, anything like that, and we can actually do a better job of calculating the water balance. So we've recently completed this revision to the model for California to incorporate 65 vegetation types that are calibrated. And the goal is to further improve estimates of recharge to support ongoing efforts corresponding with California's Sustainable Groundwater Management Act, where everybody is now having to comply with indicating that they have sustainable management of their groundwater resources. And so we've been able to calibrate for all of these locations across the basin where there are some kind of current estimate of recharge. So in summary, water balance modeling can be used to inform resource managers about how their watersheds work and where they're likely to change with future climates. And finally, resource management considerations. So we would suggest that you need to manage your resources for climate resiliency. And to do that, you need to understand the implications of a future climate with increased extremes for your watershed. What about declines in snow? How will earlier springtime snowmelt impact your stream flow? What should you monitor to understand conditions and recovery from drought? Keeping the water in the watershed is really critical. Healthy soils hold more water, reduce landscape stress and wildfire, and increase net primary production. You need to know where your high recharge potential zones are. Groundwater is key to drought resilience. Optimize your forest structure to reduce ET. You're going to enhance base flows and store more carbon. And spatially distributed water balance estimates can help provide guidance for prioritization. I hope that we have shown. That's my last slide. Are there any questions that we can address?
Thank you, Lori. We're starting to get a few questions from the audience, and just as a reminder for those on the line, we're going to ask that for today you type in any questions you have in the chat box on your control panel, and you may need to click on the red arrow to kind of expand your control panel to get to that chat box. But I'll go ahead and start off here with the first few questions that we've received. So kind of jumping back to the beginning when you were talking about the model itself, does the model incorporate underflow and input from groundwater? And could you just speak a little more about that?
No, it doesn't. It doesn't. It's grid-based. So we're assuming, we can only assume so there's no transfer of water between grid cells. What we do know to be able to try to characterize that underflow is looking at stream flow out of adjacent basins, for example. And if your water balance is high in one and low in another, we know that water is actually flowing under. We did some calculations in the upper Great Basin. What was the name of the?
You post-process underflow and flow from the groundwater system.
Oh, okay, yeah, all right. Yeah, we do. When we post-process the data, we're not getting underflow from adjacent basins, but we are calculating base flows. So we get even though we're not routing it on the surface in the model itself, the post-processing allows us to match hydrographs so that we can characterize surface flows and base flows and groundwater. Does that help?
Yeah, I think so. And if anybody has follow-up questions, please feel free to type those in. But another question here, kind of going to the example of fire that you gave towards the end of your presentation, what was the type of vegetation cover in that example?
Oh, this is Southern California chaparral. So it turns out that it's a very flashy system, and because rain comes in and really quickly, so it was very difficult to try to tease out the different processes in this system because it's so arid and flashy. But yeah, it's all chaparral, and one of the things when you lose your vegetation there, it's very uncertain what kind of vegetation is going to come back, whether or not you're going to end up with shrubberies or you're going to end up with grasslands or what have you. So it's a challenging place to do hydrologic research.
Great, thanks. And then a question here for this last slide that you have up. You've got the bullet point on optimizing forest structure to reduce evapotranspiration. Could you give an example on that? And then just let me give you a little more clarification about this question before you jump into that. It says, will this take into account, understory roles in the forest, for example, and the influence of turbulent transport through canopies, for example, and pointing out that thinning could enhance warm, dry air to dry up the understory fuels?
Well, there's all sorts of studies that have been done to show that when I say optimizing forest structure, I'm talking about taking out the small trees and leaving the big trees, and so that it's like removing a lot of the understory, and that reduces evapotranspiration and you actually have shown to be able to get base loads. Now, all of those details of the local microclimate we don't simulate with the model. I'm sure that they're important in a lot of different places, and you're going to also get different kinds of capture of snow and things like that. So there's a lot of intricacies associated with that. You know, you're running a regional water balance model. We can't really address a lot of those details, but we can show where some places it might work better than other places on a larger scale.
Great, thank you. And then our next question here, somebody points out that they know how to increase the organic matter in their garden plots, for example, but they're wondering how would you do it practically in a watershed?
Well, there's been some studies that have been going on in California. It was initiated by the Marin Carbon Project, where they're actually developing, they're creating compost in very large quantities and spreading it across the land surface, you know, a number of acres at a time, 1/4 of an inch thick. And the longer term studies, they've gone up to 7 or 8 years of studies now, have shown that you can increase your carbon in the soil, carbon sequestration, and increase your soil holding capacity by doing this. Now,
that carbon activates the soils so that they produce more carbon.
Yeah, so it's sort of a feedback mechanism where it makes the soils start storing more carbon. So you're getting more, as you increase the soil water holding capacity, you're getting more growth of plants, and so you're getting more roots, and it's a big cycle, and it actually increases organic matter over time, even with the one application. They're hoping to be able, there's a lot of efforts going on in California at the state scale to try to encourage conversion of lands into either optimizing your grazing strategies so that you can increase your organic matter, or actually adding carbon at a very large scale. And lots of people are calculating, trying to see how this can be done, encouraging and giving incentives for doing this work. At this point in time, I don't know how realistic it is to do it on a really large scale. It's been done for, you know, many acres at a time, and there's people that own you know, hundreds or thousands of acres that have been able to do things like spreading ash on their soils, just broadcasting it over very large areas, and then keeping their grass green into the drought while all of their neighbors' cattle were being sold off. So there's anecdotal evidence that shows it works, and there's local evidence that shows it works. So take your garden, you know, make your garden processes go bigger and better.
Thanks. We've got 2 more questions that have come in here. The next one is also kind of related to management application, and it is, do you know if there are prescriptive livestock grazing management strategies that would enhance water soil holding capacity? Yes,
absolutely. The Carbon Cycle Institute is, if anybody wants to just Google Carbon Cycle Institute, there's a whole series of best practices that they've worked up with, working with the NRCS and others to come up with best management practices for developing healthy soils. And whether it's ranching or farming or whatever, it's a very elaborate set of guidelines. There's also a spreadsheet kind of model that you can work with called Comet Planner, and it allows you to put in the management that you're doing on your land with whatever the acreage is and the specific details of your location, and it will calculate the carbon sequestered for you. We, as part of our project, have tried to calculate what the water benefits are.
Okay, great, thank you. And then this next question here is, have simulations of soil loss owing to erosion after fire been considered in the future modeling scenarios? And the commenter kind of goes on to say they wanted to note the recent paper by Sankey et al., which shows an increase in fire in response to climate warming. And they kind of noted that it's hard to increase soil moisture after your soils are degraded or lost, owing to widespread erosion. And so, any comments on that?
Well, it's a very good point, and it's very common in a lot of places. So the wildfire causes lots of degradation typically, and oftentimes you have to go back and actually start from scratch and regenerate sites. Bring in new vegetation and start the whole process over again. It's one of the issues that contributes most widely to your water quality, downstream water quality post-fire. I agree with the comment.
Okay, it looks like at this point we've gone through all the questions that came in from the audience. Rick, I want to just check with you. Sometimes I know you have folks with you in attendance. Are there any questions from your group?
Not at this time. But I just wanted to share that this has been a very exciting presentation. Thank you, Lori, for being with us today and sharing this information. Just for folks on the phone, we will make a recording of this presentation available on our website either tomorrow or early next week. And if you have questions, please feel free to reach out to Dr. Flint or myself or Dr. John Tull, our science coordinator. Their contact information is on the screen now. And last but not least, we would really like to know what you thought of today's webinar. So we invite you to please take a short 2-minute survey that will appear on your screen as you log off here today. Your feedback is highly valuable to us and helps us to plan and to improve our future webinars. Well, Lori, thank you once again. Did you have any type of comments before we sign off for today?
I think that the kinds of tools that we're developing can be used in so many places. I always am welcoming feedback for how people can consider how to use this kind of information. We're spent a lot of time iterating back and forth with landowners and land resource managers to try to understand how best to provide either data or interpretations of data to help people make the best management decisions.
Well, that's great advice, and we look forward to working with you and seeing future results. Well, thank you once again. And thank you all for tuning in today and learning about this very important work. I wish you a very good day, and we'll see you next time. So long.
Thank you.